Hey mathletes, welcome to a little mini video on something we're going to call the tangent problem. Now, maybe your first thought is when you see that, the word tangent, you think, hey, I've been talking about tangents in trig. Yeah, definitely we've been talking about tangents in trig, but we're going to kind of go back a little bit in history and we're going to talk about what tangent actually means and where it comes from. It doesn't quite derive um, where we have been using it, but that's okay. We'll talk about that as we go. Okay, but before we even do that, I want to go all the way back to 10C, friends. And I've drawn us a nice little graph of something we would have had in 10C, a nice little linear looking graph. And you can see I've labeled a couple points, x1, y1, x2, y2. Okay, what am I going to do here? Well, I want to start off by talking about the slope of this line. So if you remember to find the slope of the line, what we would do is we would find the change in y over the change in x. And I'm going to draw just a little right triangle in here just to demonstrate that. That's really what we're doing, is we're finding the change in y and the change in x. There's that little triangle there. Okay, so our slope, which remember we denoted as m, is y2 minus y1 over x2 minus x1. And you're like, yeah, okay, I got that. I remember slope. Okay, later on, we're going to talk about slope as the change in y is the change in x. So we're going to call it delta y, delta x. And so you're going to see a little bit of different notation later on in calculus, and we're going to write it like that. And that's going to be really important for us later on. Okay, but why is he talking about slope again? I get slope. Well, here's the important thing about slope in grade 10. This line, the slope is constant everywhere. It doesn't matter where I drew those 2 points, the slope is constant because it's a straight line. The other reason I want to think about my slope in grade 10 is that this is the rate of change at any given moment of this function. It's the instantaneous rate of change. All right. Okay, easy. Now what I want to do then is I want to think about any of the other graphs that you've seen since grade 10, such as we'll go to grade 11 and a parabola. Now, if I say, what's the rate of change on this graph? Well, you can't tell me because the rate of change is always different depending where we're looking. If I have a point here, 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 the rate of change is always changing at any different moment. So this is going to be the big problem for us in the first half of calculus. How do we find the rate of change when it's always changing? What we're going to do to solve this problem is we are going to draw something known as the tangent line. The word tangent means we're hitting something at just one point. It's intersecting at just one moment. This is the tangent line. And we are going to use the tangent line to tell us the instantaneous rate of growth or change. How are we going to do that? Okay, well, how we're going to do that first is let's look at another parabola. You can see I've got 2 points drawn here, the green guy and the blue guy. What we're going to do is if I want to find the instantaneous rate of change at the blue point, what I'm going to do is I'm going to draw something known as the secant line. A secant line right here is a line that crosses across a graph and hits it more than once, twice to be precise. Now, that's the average rate of change. So the secant line is the average rate of change of those 2 points. And you can see the slope is calculated there. It's 4.7. What we are going to learn to do in this first unit is we are going to learn what's going to happen when we drag this other point, and notice the secant line. Notice how the slopes of the secant lines are increasing as we go. Watch what's happening. As I drag that point closer and closer and closer to this other one, the secant line turns into a tangent line right there. So what this slope is, m is equal to 13.96, very precise. That is the instantaneous rate of change at that moment. So our goal in the first unit, and this is a big goal, friends, as you're learning what limits are, our goal is to find the instantaneous rate of change. And how we are going to find the instantaneous rate of change is we are going to use secant lines, and we're going to find the slopes of the secant lines. And as we move our points closer and closer together, the slopes of our secant line will approach the slope of our tangent line, and the slope of our tangent line is our instantaneous rate of change. Okay, it's a very conceptual thing to think about, but that is going to be your goal, which we're going to figure out in about 5 lessons from now. Okay, so the tangent problem is what you're working on today. I hope that helped demonstrate a little bit visually what's going on. See you another time.